Okay, so yeah, my name is Raphael, and actually this presentation is really interesting because it's the opposite of the last presentation. Now we have a power system. So, and what is a power system? For a little general definition. So, a power system is the electrical system that we have generation, transmission, distribution, and demand. And from the nonlinear stability analysis, we are looking at the transmission and generation side. We are the distribution and demand side. We are assuming that they are loads in our analysis. And in electrical engineering, we usually call the nonlinear stability analysis the transient stability problem. And we call that the transient stability problem because we are dealing with large disturbance in our system. Large disturbance such as losing a transmission line, losing having large short circuits. And so if it was on a small disturbance, we could use it like a linear analysis, and then we would call small signal analysis. Since we are studying large disturbances, we use the transient because it's a long time of simulation. And how can I express mathematically what is the transient stability problem? So the main idea here, different from a normal stability analysis that we will use one set of differential equations, we are actually dealing with a set of three because we have a pre-disturbance. Our system is working, so it is stable, and we have a disturbed system that we apply a disturbance there, and we assume that this disturbance lasts for a time, and we call that the clearing time. For the from the electrical engineering side, we call this a fault. So we have this clearing time that I put here like TCL. And then we have the post-disturbance system. Our states in our analysis usually are the angle machines and the angular speed of these big machines, rotors that are generating power. And so how can this set of differential equations are coupled together? So the main idea here, pre-disturbance, our differential equations, they are at equilibrium. So x dot is going to be 0, and we have an equilibrium point. Our disturbance system doesn't have an equilibrium point, but the initial solution of that system will be the equilibrium point of the pre-disturbance. And the same thing in the post-disturbance, but the post-disturbance, we can assume that it has an equilibrium point, and we can assume that we don't know if it is the same as the pre-disturbance one or not, but we assume that it has. And the initial solution of the post-disturbance system will be the same. It will be the solution of our disturbed system at the clearing time. So they are coupled together. But how can we evaluate the stability here? It's very hard. And so what do? We use an idea from dynamical system that's called stability region. Sometimes it's called basin of attraction or area of attraction. It depends on the algorithm or the area that you are, or the subject that you are studying. So the main idea here, the idea of the stability region is given an equilibrium point. We want to know the set of points, initial solutions there, that as t goes to infinity, our trajectory, our solution trajectory is initiating on those points thanks to the equilibrium point as t goes to infinity. So if you have the stability region of our post-fault system, post-disturbance system, and we know the trajectory, and I put here Fortulan trajectory, but is the disturbed trajectory, is the same meaning. And if we know the Fortulan trajectory and we know the stability region, and in particular, we know if when the fault is cleared, when we don't have more disturbance, if it is inside our stability region, then the post-fault system, the post-disturbance system will be stable. The problem is finding stability region, it's not that hard if you think about it, because I can use some kind of computer and run a lot of simulations and try to find it. As for several points, I run the simulation, see if it goes to the equilibrium point. But the problem is, for power system, our measurements, our demand is not static. We are changing. And at each 5 minutes, our control center receives new information and it needs to update and evaluate the stability of our system. So it's impossible for us to do it in this kind of naive solution in real time, or as real as it can get. So what do? We find an approximation for the stability region. And this approximation doesn't need to be really good at all region of space, but it actually needs to be really nice for the fault zone trajectory, for the disturbance system trajectory. We need to find one approximation that it gets like the boundary of this approximation, the boundary of our stability region is really similar at the trajectory, when the trajectory intersects. And how we do that? I mean, now we have a problem. Now we know that we need approximation, but how can we find one? So what we do is we use the Lyapunov's stability and the invariance principle that allows us to use energy functions to find an estimate for the stability region. Lyapunov stability and invariance principle, they use energy functions or Lyapunov functions to study the stability of dynamical systems. And from that theory, we know that we can find an approximate for this stability region as a level curve for a Lyapunov function or energy function. So now we need to find L. So let's assume that if we have L, we can find the stability. We can evaluate. If we can determine L, we can evaluate our energy function at TCL. If our energy is less than L, so it is inside the stability region, and then we are safe. The problem is, how can we find L? So there are several ways to doing so. This one is a more like physical motivation based example. For example, let's assume that we have a ball here, and we want to see if this ball are going to apply a disturbance there. The system at rest, so at equilibrium, we apply a disturbance, and we want to see if this ball is going to fall or not. So the main thing here, so the ball can fall or it can stay around the equilibrium, and how physically, how can we calculate that? So the main thing here, if our disturbance energy there that we applied at the rest, if it is less than the difference of potential energy there, then if we assume that, then the ball are going to stay inside this basing. And this is the main idea. The method is called PEBS, that is called for as acronym for potential energy boundary surface. So we are using the potential energy of our energy function, the potential part of that function, to find the value L. And so that's okay. So now we can solve it, for power system, for common power system, we can do it. So, but nowadays we have an increase in uncertainty in our system. We have solar energy generation from wind, from the sun, from even waves, and they are very hard to model. We can model that probability distribution for them, but it's actually very hard to include them in our analysis. But we must do so, because this kind of intermittent generation, because they are increasing in size in our power system, we need to include them in our models. In this research, what we did, we used something called in the uniform invariance principle. The main idea here, let's assume the invariance principle uses a function f x dot f of x and v of x. The uniform invariance principle, there's a second argument for the function f that is lambda, and lambda is going to be the parameters of our system. And then we are going to include in our model all of those uncertainties in lambda. And it's very similar to the invariance principle, the uniform one. The main difference is that we need to find a of x and b of x and c of x so that these inequalities are satisfied for any kind of lambda combination that we can have in our system. And a main thing here, so if we can, the result of the invariance principle, it shows that we can construct sets, and this set is going to be A of L, B of L, E of L, A of L again, B of L again. But the main result here is that is the same result as in the variance principle, that we need to find an L to estimate, and we need to find A of X and B of X. This is the main thing here. And so, and we can even try and create a uniform version of our potential energy boundary surface idea. And so the main idea here, instead of using the function v of x, because v of x is going to depend on lambda now, we are using the potential component of a of x, because a of x now is independent of lambda. And we are going to find this maximum of potential energy of a of x, a p of x, the potential component of a of x, and we are going to evaluate v of x. V of x now is going to be evaluated at the b of x that is the highest value that v of x, the energy function, can assume given any combination of our parameters. And then if we do that, the result of the theorem here is that the post-fault system is going to be stable for any combination of parameters lambda. And so, okay, that's really nice and really amazing. But the problem is now that power systems are really large. I mean, continental size for places like US, Brazil, and China. So trying to find this kind of functions, A of X, B of X, given any kind of uncertainties that we have in our systems is really hard, and they are not trivial. In this research, what we do is we use something called interval arithmetic. And we know that maybe it's not the best solution in a sense, because ideally, this kind of distributions, this kind of uncertainties will follow, I don't know, maybe a Gaussian distribution, normal distribution. It will not follow this kind of uniform distribution between a maximum and a minimum value. But the problem is we need to evaluate things fast. If we try to do it, evaluate using Monte Carlo or something kind of sampling algorithm, we don't have enough time or computer resources to do so. So interval arithmetic allows us to use simple rules of algebra to find really nice estimates for the maximum and minimum value of operations there. So we have intervals. So now our uncertainties will be modeled like intervals. And we can have even functions of intervals. So the main definition here is the function of an interval is going to be the union of our function applied at each point of our set x, our interval x. And so, and the main thing here is that a function of an interval is actually going to be an interval. And so now we can find using this, and I use lambda here as this now is an interval vector, is not more a random vector. So it's going to, we can find A of X and B of X. And by interval arithmetics, we know that they are going to be really estimates, and they are going to, by the fundamental theorem of interval arithmetics, actually we can prove that by using this kind of result, our inequality is required for the interval, for the uniform invariance principle will always be satisfied. And then we can find C of X. And C of X is not actually used for in our analysis, but is only used to prove our theorems that I'm not going to prove here because I don't have time. And so now I show here the easiest example that I can imagine. The easiest example is like a one machine connect to an infinite bus. The infinite bus is representing like a very large power system. So it's something similar like you connecting a very small motor in your power outlet. This is not going to affect the stability. So the stability of your system can be unstable, but the overall system cannot be. And so these are the kind of differential equations that we have in power system. This is the energy function. And I use this kind of, I use only uncertainties on the post-fault systems only for simulation, but I can use this formulation in general. I can even use difference for the pre-fault, for the fault on, for the post-fault systems. They can have a different set of uncertainties, and the theorem will work, the simulations will work also. And so if we do that, if we plot our results in time only for us to see this, actually here, instead of seeing if the system was unstable or stable, I calculate the maximum value that my fault can stay on the system. So I calculate when the trajectory of our fault on system, how much our system can stay on fault. Disturbance can be applied before exiting the stability region and being unstable. The post-fault system is going to be unstable. So here is only for mentioning. So I have this is going to be the critical time. This is going to be the critical energy. And these are the results of the A of B of X, A of X, AP of X, and BP of X. This P is the potential parcel of the energy of our energy functions. So yeah, that's it. This is like a main overview of how can we include, how we are doing to include uncertainties in our analysis, and how can we use the theory of dynamical systems, energy functions, and Lyapunov functions to study stability of real and large and critical systems. Okay.
Brilliant. Thank you very much. Okay, so we've got plenty of time for questions. So let me find my chat box. I keep getting it lost because I keep keeps going behind the screens and watching it. Yeah, so if anybody's got any questions, just pop them into the chat box for me. I must say I really enjoyed all the diagrams. I'm a sucker for a presentation with lots of really nice diagrams, so I appreciated the effort put into those. So Demetrius has a comment saying the hardest part is usually finding a good Lyapunov function. I'm sure I butchered that.
Yes, actually, this is amazing question because this is this is the problem. And so for the one machine system is actually really easy because because it's a physical system, we can do kinetic part and a potential part here. But the problem of for very large systems, because we are dealing they are connected to each other. So when we are calculating the potential part, we actually have a path-dependent integral there. And so the Lyapunov function, actually, we can prove that we cannot find a Lyapunov function for larger systems. What we do is we do, we do like a numeric approximation there. And we do this kind of physical interpretation, thinking about how the system operates because this is a physical system. There's a rotors there, so we do this way. But yeah, actually, it's not 100 mathematically. It's not 100% correct.
Wonderful, thank you. Okay, so we've got some questions coming in. It's nice to see people's brains are still working. So what's the meaning of PEBS?
Okay, PBS is the potential energy boundary surface, because we are using the potential energy to find the approximation for the stability region. That's what the guy called when he invented, I think it was in the 60s. This one is a very old idea, but it works until now, surprisingly.